To everyone. My name is Fernando Gont, and I will be presenting new features in the SI6 Networks IPv6 Toolkit. As an introduction about myself, I work as a security research for SI6 Networks. I'm very active at the IETF, working on the standardization of a number of protocols, but focusing a lot on IPv6. I have quite a few active internet drafts there and some RFCs too. I'm the author of this toolkit about which I'm going to present new features. And I'm also the listed admin of the IPv6 hackers mailing list that you're probably subscribed to. You can find more information and links to the publications and so on in my website, which is very dated, so to speak. So what is this presentation about? It's about, this is a nice quote that I read from Ken Thompson, which for me kind of describes some of the presentations that I do, that at times you get to spend a lot of time on different things. It could be like a standard, a tool or something, and at times it's nice to, to explain what you did to colleagues, to some extent to show the reason, oops, still working. To show or to try to explain why you did what you did, but also at the same time, because usually you can get feedback from colleagues, and that helps improve your work. So this talk is essentially about new features in the SI6 Networks IPv6 Toolkit. Stuff that will not be covered in this presentation is anything related to the World Cup. I'm from Argentina, so it was a very sad year next year. I already got choked from Eno when I arrived here, and so I'm not going to talk about football during the whole week. It was already a very sad year last year, so forget it. You were lucky. As a kind of introduction, as I said before, this is a presentation about new features in the IPv6 Toolkit. As a brief history or as a brief description of this toolkit was originally produced as part of a project that I was working on for a defense organization in the UK many years ago. And maintenance and extension was taken over by me for SI6 Networks. A funny story regarding the toolkit was that it originally wasn't intended to be formally released. And I was once talking with a colleague, and this colleague told me, well, but the toolkit is publicly available. I said, no, we never released it. Yes, it's public. No, it's not. Yes, it's public. No, it's not. And apparently some company decided they liked the toolkit and they posted it online. So that's why it ended up being released, which on one hand, let's say that was unfortunate. But on the other side of things, the toolkit leaked out and it was released somehow already. That gave me the chance to actually take what was supposed to be like a private project and make improvements and be able to release those improvements. But that's a funny story of somehow how the first version of the toolkit was released. So we didn't release the first version of the toolkit wasn't released by us, so to speak. As a brief description about the goals of this toolkit, it's essentially a toolkit for security analysis and troubleshooting of IPv6 networks and implementations. It's not really an attack toolkit, so you can use this toolkit for many other things other than attacks, like, for example, troubleshooting a network. Among the goals was to have clean, portable, and secure code to the extent that was possible. And that's not because I really wanted that to be the case, but since this was done as part of a project for that organization, we couldn't really ship crappy code. That doesn't mean that the code is as good as it should be, but let's say we really intended the code to be, let's say, decent to some extent. There are some things that we did, for example, which are, I think, nice details. For example, the tools, for many things, they need super user privileges, but they release those super user privileges as soon as they are not needed anymore. And that's something that, while I was exploring security tools, it's kind of let's say, ironic, but most security tools, they are security tools, but at times they are, coded in insecure ways. So most of the security tools that you probably are using every day, they run as root for their, for their whole life, even when they don't need that. So that's among the details that we were trying to pay attention to. Also, we try to produce good documentation. Probably the most boring and tedious part of working on the toolkit is writing the documentation. Even worst of all, the first manual pages were like TXT or PDF documents. And then when we tried to produce like a package, we had to convert that to the TROF or ROF or whatever you want to call it, the man page format, which is for me not a nice thing to spend my time on. But when I look at the manual pages, probably I spend like quite a share of time on the manual pages, so please read them. Not for the manual pages themselves, but because we spend a lot of time on that. Continuing with the introduction of the toolkit, we originally tried to support at least all the BSDs or the most popular BSDs on Linux. Then we incorporated macOS, and in this last release, we incorporated OpenSolaris. Probably if you have not been coding like lately, you say, well, that this guy is talking crap. I mean, these are all like Unix-like systems. So it's probably like a piece of cake to do this. It should, but in practice, it's not. So when you are coding the tools, sometimes you have to, reorder the way in which you include the, like the include files. There are some functions that are supported by one operating system, but not by another. With macOS, first of all, I don't have a Mac myself. So that means that I have to have someone else try to compile the tools and run them, and they report errors. And I try to fix the errors, without even being able to try that myself. But the guys from Apple do, funny things. Like they have version, let's say 1.4, which supports something. Version 1.5, they remove that support. Version 1.6, they include that support again. So it's like a pain. It's a pain. And supporting OpenSolaris was a little bit of pain too. And but to some extent, that of supporting multiple operating systems, I think that at the end of the day, it helps to improve the code. I wish that's the case at least. The license of these toolkits, it's GPL, it's free software. There's a Git repository for the toolkit, and yeah, so that's the homepage and the Git repository. Some comments about what the idea behind the toolkit. Usually people when they download the toolkit and they try to run some tool and they see that the tool says, well, you have not supplied this or that information, and they get extremely frustrated. To some extent, that's intended. So this toolkit is not meant for you to just run some command and have the tools perform some sort of attack that you don't understand. But actually, it's kind of like meant to be an interface between you and the network. So if you know what you're doing, the toolkit is going to be helpful. If you have no clue about what you're doing and try to run the tools, probably with most of them, you're not going to be able to do much, okay? At some point, and unfortunately, when you spend time on code, I mean, it's always nice to have people use it. So we have been having like an internal debate regarding whether we should include some sort of wrappers, like script kiddie versions of the tools, like with the, let's say, more popular commands. So so far we haven't, but I mean, eventually we would probably do that. What else? So when it comes to the tools, these are the tools that are currently supported by the toolkit. With many of these tools, they are tools that essentially allow you to send specific packets. So for example, if you take a look at TCP6, well, it's obviously a tool that allows you to send arbitrary TCP segments on top of IPv6 packets. So NS6 is for neighbor solicitations, NI6 is for neighbor advertisements, and so on. And there are a few other tools which probably perform like a more complex task, or you could think of them more of as applications. For example, Scan6 is an address scanner. There are like Address6 is a tool for analyzing IPv6 addresses and so on. These are the other tools that the toolkit has. And I'm going to present what we have incorporated in version 2.0 of the toolkit. Actually, this, I don't know if I could use in bad analysis. Version 2.0 could be like, if you like Guns N' Roses, this could be like Chinese democracy. So which means that it was delayed for a long time. and probably it should have more stuff that it has, but whatever, it is what it is. So you could find, like, in the same way that in Chinese democracy you can probably find like a couple of songs that are okay, well, the same thing here. We have a couple of new features that are okay, the other ones, well, whatever. Overview. So what's new in this new version? First of all, lots of bug fixes. So this is the kind of thing that I don't know if you are proud to say, because if you fixed a lot of stuff, that means that a lot of stuff was broken. But truth is that lots of stuff was fixed. It's extremely painful to work on tools that let's say that are able to deal with arbitrary IPv6 packets, and the reason for that is that you need to operate at the link layer, essentially. So, for example, if I want to build a tool that sends, let's say, an ICMP packet, in practice, what I need to do is build everything from the link layer up to the ICMP layer. So I need to be able to route the packets. I need to know on which interface to send the packets and so on. For many reasons, one of them is that in the support that V6 has for raw sockets, it's kind of like crappy. For example, you cannot spoof IPv6 addresses, at least in a portable way. So if you want to spoof IPv6 addresses, you have to produce a link layer packet. And that means that essentially you have to, essentially code an entire IPv6 stack inside your tool. So eventually I was thinking, well, I already did neighbor discovery, I already did TCP, I already, did the routing part. So I probably could, start my embedded operating system or something like that with V6. It's not that I like it, but it was painful. And not to mention, of course, that since you usually have to deal with the internals of different operating systems, obviously every operating system does things in a different way. So there you go. So many of the fixes had to do with that. We also included support for Open Solaris. If you ask me, I don't think I could provide a good reason for supporting Open Solaris. We just did. I guess that probably the only motivation is to make the code more portable, and that's it. Tools that are new in this version of the toolkit: Script 6, Black Hole 6, UDP 6. I think Path 6 that I'm going to present later is new too. And there are new features in different tools, such as there was a TCP6 tool for playing with TCP segments. It has additional features. And that's also the case for Scan6. Okay, so let's start with address scanning. Probably, if you look at the Scan6 scanner that we have in this toolkit, is the most comprehensive address scanner that you will find. Probably not because we did an extremely good job, but actually because when you look at other address scanning tools, they are not so much elaborated. Previous versions of Scan6 could already, for example, you could tell the tool to exploit a specific pattern in addresses, and the tool would do that. And what we did in this version of the tool is, incorporating a feature that does automatic address scanning. So what the tool does is, for example, if you provide the tool with a domain name or an IPv6 address, the tool will automatically analyze that address and will try to infer what's the pattern that is being used by that address and only target that address pattern, okay? So this is the way in which you could run the tool for using the automatic smart scanning. You essentially just provide a domain name, and by specifying /64, that means that you want to target that network, or you can just specify an IPv6 address and specify that it's a /64. As I said before, if you do that, the tool will target the specific address pattern being employed by that side. Let's see if we can make this one in here. Where was this one? So, for example, if everything works fine, we could do something like, let's say, so for example, what I stopped the tool, meanwhile, and I, let me try to expand this so that it's easier to see, okay? So what I did, I specified let's do this again. So oops. So I just selected some domain name, okay, netbsd.org, and then the tool automatically analyzes the address pattern that, that domain name has, and then only targets that part of the address space. So in this case, you can see that on the top, it is trying like what we call small byte addresses, which means that it tries numbers, on the last couple of 16-bit words, it tries small numbers. If you go to, let's try something else. Let's see. Oops. So if you look here, you can see that the pattern that the tool is trying up there is different. Okay? And that's the case essentially with every domain that the network is a little bit, or my connection to this system is a little bit slow. But essentially, the bottom line is that, by specifying a domain name or an IPv6 address and a /64, the tool can automatically detect what's the address pattern that it should target. In previous versions, we had a tool, address6, which could help you to identify the address pattern, but you had to, let's say that you had to specify the address pattern yourself. So you had to grab the address, run address6 to analyze the address, and then, input the appropriate information to scan6. So with this version of the tool, you don't even need to do that. The tool does that automatically. Of course, what the tool does is kind of like reuse the code that we use for the other tool, address6. Port scanning. In this version of the toolkit, we added we incorporated some, basic TCP and UDP port scanning. So if you employ this option, port scan, you can select, for example, whether you want to scan TCP ports or UDP ports. And the idea is simple. You can specify like, the protocol and a port range. And you can also specify the TCP, in the case of TCP itself, you can specify the TCP scan type, okay? As a brief reminder, this could be an example, right? In this case, we are specifying that we want to scan for TCP ports and in the range from 1 to 1024, and the scan type is going to be like a scene scan, which means that we are not we are not doing the full three-way handshake, but just sending sync packets and waiting for the response. As a kind of overview, because it's going to be useful for some of the next few slides, this is a TCP connection establishment in a nutshell, so to speak. So if this is the host that you want to scan, when a connection is, when a port is open and you are able to establish a connection, what happens is that you send this should probably work. There you go. You send a SYN packet, and then you receive a SYNAC packet from the target system. Typically, if you, let's say, if you do a traditional connect scan, that means that you want to, perform the full three-way handshake, which is slow. So usually, what you will do is just use these first two packets, and that is what is called a SYN scan, which means you send a SYN packet to the target, this host, and you wait for the response. If you receive a SYNAC, which is this packet, that means that the port is open, and if instead of receiving this packet, you receive a reset, that means that the port is closed. When it comes to the connect scan, which means using the full three-way handshake, that port scanning technique is slow. because it requires you, to exchange those 3 packets. And at the same time, it's also to some extent undesirable because since you establish the full connection, that means that the application on the other end gets to know that you try to connect to it. So we didn't actually, implement this in Scan6. So I don't think there's like a valid reason for which you use a full connect scan. There's the SYN scan, which is the one that I was mentioning before, which is quite simple. You send a SYN packet, what I was showing before here. And then you wait for the response. If you get a SYNAC, it means the port is open. If you get a reset, that means the port is closed. It is fast. A nice thing is that it doesn't tie resources on your end. And the reason for that is that we are spoofing the packets. So that means that whenever we send a SYN packet to the other end, we are not tying any resources on our own local system. So we could be like, scanning like thousands and thousands of ports at the same point in time, and that doesn't tie resources on our end at all. And this is a technique that we implemented in Scan6. There is also what is called the fin, null, and Christmas scans. These techniques, they don't require you to perform the full 3-way handshake. Essentially, the idea is that you send the packet without the ACK bit set. And what the specifications say is that if the port is closed, you are going to receive a reset. And if the port is open, you are not going to receive anything, and there's going to be a timeout. Okay? It's rather slow because, since one of the options is that you are going to get a timeout, you need to wait for some period of time as opposed to just being able to, react to any response. In the case of the SYN attack, in the case of the SYN scan, you get a SYNAC or you get a reset. So one way or another, as soon as you receive a packet, you know whether the port is open or closed. In this case, if you don't receive anything, you still need to wait. We have implemented these, all of these scanning techniques. If you wonder why, it's called fin, null, and Christmas scans, well, they are actually the same thing. This is not very much documented. So years ago, when I was trying to document lots of things related to TCP, I had to dig into this. At the time, I expected that these techniques were totally different. But the idea behind these 3 scanning techniques is that the ACK bit is not set. So in the case of the fin scan, the ACK bit is not set, but you send the fin bit. In the case of the null scan, there's no bit set. And there's the Christmas scan in which you set the fin bits. And I don't recall if there was some other bit set, but there could be other options, like for example, setting bits that are related with ECN, like explicit congestion notification, which don't have like a specific name, but they will be variations of these same scanning techniques. Let's see. So, So in this case, I'm running the, the port scanner on a virtual network that I have on my computer. And these are the results that you get, like pretty similar to what you get in Nmap, okay? So far, the only caveat when it comes to the use of port scanning in the Scan6 tool is that right now, at this point in time, it supports scanning a single IPv6 address, okay? So that means that you should run, if you want to do, let's say, a port scan of a lot of systems, you should first run Scan6 for finding the alive nodes, and then you should run another instance of Scan6 to do a port scan of each of those IPv6 addresses. In the next version, my idea is to be able to support scanning multiple, doing a port scan of multiple systems at the same time. The only tricky part is that if you are scanning all of those systems in parallel, you kind of need to reorder the responses that you get because you are scanning everything in parallel, but of course when you print those results on the screen, you want them to be ordered, okay? So that's the tricky part. Tools such as Nmap, as far as I recall, what they do is they consume quite a lot of memory because for each system that they are scanning, they reserve resources on the local system, and that's exactly what I don't want to do, okay? Not because it's bad, but actually because it requires a lot of memory. So I already kind of sketch the way in which I'm going to implement this, but the idea is that you shouldn't, the scanning tool shouldn't, tie lots of memory on your side when you're scanning lots of systems in parallel. But in any case, what you do so far is, again, run the scan6 tool, find the nodes that are alive, and then you run a different instance for, for doing the port scan. Okay. Other tools. So there is this tool, TCP6, which was present in earlier versions of the toolkit already, as far as I recall. And this tool was really, developed out of frustration. At some point in time when I was playing with V6, I said, well, where is a scene floater for V6, which is an extremely trivial tool. There wasn't any, okay? Something as trivial as a scene floater wasn't publicly available. Mark Oise of THC, he did an implementation of a scene floater too, and at the time when I was working on this, I think he had not published his scene floater yet. So that's how I started working on TCP6, but then it was kind of like a deja vu, so to speak, because years ago when I got involved in protocol and IETF stuff, most of the work that I did at the time was focused on the TCP protocol, and there were many things that at the time I wanted to test, but you didn't really have useful tools to be able to check that. If you know a little bit about TCP, for example, there are things like TCP simultaneous opens, and if you want to check, for example, whether a system supports simultaneous opens, there's no trivial way to do that because there's no tool that allows you to do that easily. So I ended up, incorporating lots of features to this TCP6 tool, not just for being able to perform attacks, but also to, test things that at that point in time I wasn't able to test. Another thing that was quite interesting on my side was that, almost, let's say, 5 or 6 or 10 years ago, I had published this document on TCP security with different ways in which you could attack a TCP implementation, but at the time I hadn't published any TCP tools based on IPv4 to perform those attacks. And in many cases, there were no publicly available tools to perform those attacks. So essentially, I did a tool that now can perform those attacks that I described years ago for the IPv4 wall, but that in many cases they had not been exploited or for which you didn't really have a publicly available tool to exploit them. So before I describe some of the things that you can do with TCP6, I'm going to have a couple of slides with some TCP fundamentals, so that if you're not that used to the TCP internals, you can follow the rest of the slideware. First of all, there's what is called the TCP three-way handshake. So the idea is that if you have two systems that want to transfer information by means of TCP, you have to perform what is called the three-way handshake, which involves the exchange of usually 3 segments. So this is the host A, that is opening the connection. It sends a SYN packet, then host B sends a SYN-ACK packet, and then finally host A sends this acknowledgement packet. So the idea is that once those 3 segments have been exchanged, the connection is established on both sides of the network. Just for the time being, I mean, before I actually describe this with tools, one of the things that you could probably think of is saying, well, if you just told me that when you establish a connection, you exchange these 3 packets and then you get the connection in the established state here and here, probably you could say, well, what if I was able to establish lots and lots of connections, right? Of course, in order to keep a connection alive, you have to keep state on your system. In order to keep state, you need to use memory of some sort. and since memory is a finite resource, eventually you will consume all that memory. Now, let's say if you were to try to perform this attack in the most trivial way, you would probably employ like the sockets API, like the connect function, and issue many connection requests on this side to create many connections. Now, the problem in that case is that if you are really also keeping state on your side, then you're suffering the effect of the attack yourself. I mean, you're establishing a lot of connections with the target system. Now, yes, this system now has to handle lots of connections, but you're going to handle all those connections yourself. So probably you will kill yourself earlier than you will kill the server, okay? So the idea here is how could you possibly, establish lots of connections here without having to tie your own resources on your side, okay? So in that case, it doesn't cost you much to establish the connections, but you do tie lots of resources at the server. So that's something that this TCP6 tool will allow you to do. And then now a couple of comments about what is typically referred to as the connection termination phase. So let's say that you have established a connection, you have exchanged data over that connection, and eventually you are done with that connection, so you want to close it, okay? So the way in which you do that, the system that first tries to close the connection, which in this case would be this one, sends a FIN packet, like saying, I want to close my side of the connection, and then the other side responds like with this ACK, which means, okay, so TCP connections are bidirectional. So if I'm if I'm connecting to a different system, I have to close my own side of the connection, my sending side of the connection, and the other end has to do exactly the same thing. So this means, one way to interpret this is, I'm not going to send you any more information, and this other system tells me, okay. And eventually, some point later, this system says, you know what, I'm not going to send any more information either, and I say here, okay. So while you exchange those packets, the TCP connections on each side is supposed to transition through different states, okay? This is in the TCP specification. There's nothing that I invented here. Now, some things that you should consider, which I think I have in the next slide, is that there are some, let's say that if you are coding an application, there are states that are typically handled by an application, like the established state. Usually when a connection is in the established state, there's an application there that is transferring or sending or reading data. But in other states, such as FIN-wait2 or time-wait, it's not the application itself that handles the connection, but it is the kernel. Okay? So your application is done with the connection, but it is the underlying kernel, the one handling the connections. So you probably wonder, well, why should I care about this, or why do you mention this? Because there are certain implications when you want to use these for attacks. So let's start with a very simple scenario. Let's say that I have some server here, and I, for example, say, well, I'm going to perform like a connection flooding attack. I'm going to establish many connections with that server without spoofing addresses or anything, right? Just using my real address. If I perform like a proper connection flood and I keep all of the connections in this state established, then the application at the server will be aware about all of the connections that I have established with it. So for example, at the application layer, that server could implement mitigations and say, I'm, for example, only going to accept 10 connections per IP address, for example. And you can do that at the application layer. So the application can see all of the connections that are active at some point in time. Now, when it comes to states, such as FIN-wait2 or time-wait, these are not handled by the application itself. They are handled by the kernel. So that means that if you code an application and you try to mitigate these sort of attacks, generally, you cannot do anything about connection floods that try to exploit these states. So connection floods that try to get connections in FIN-wait2, time-wait, and so on, can only be mitigated at the operating system. Okay? That's like an important difference. There are cases in which you have, server implementations could be web servers, could be DNS servers, where they do implement mitigation for connection floodings, but they can only, mitigate connections that are in the established state. Now, if you get to somehow put those connections in any of these states, then you are bypassing any protection that those applications have implemented. So this is what I just said. Some states are typically handled by the kernel, others by the application. And again, that affects who in the target system can implement mitigation, whether that's the application or whether that's the kernel. So some features in the TCP6 tool. So TCP6 has an open mode option that essentially allows you to select how the three-way handshake is going to be performed. So you can tell the tool that you want the tool to accept connections. You can tell the tool that you want the tool to open connections in the normal way, but you can also tell the tool, for example, I want the tool to force like a simultaneous open scenario. That's a scenario, for example, that doesn't really happen in practice, but you can get the tool to do that. This is, of course, how you select the mode, and of course, you have to use any. You have to use any of these keywords, next to the open mode option. There's also a closed mode option, which is more useful for from the attacker's point of view, which allows you to select, well, first of all, to tell the tool that you want to close connections, but you can also tell the tool in which state you want the targeted connections to be in. So, for example, you can cause your malicious connections to remain in the last act state, fin wait 2 state, and so on. I mean, it doesn't really matter if you don't understand the details or the differences between all of these states, but what's important here is that with this tool, you can you can flood a target system with as many connections as you want, but also cause those malicious connections to be in any specific TCP state that you want. Typically, with the tools that you will find out there, you can only flood connections or establish connections and put them in the established state. With this tool, you can make a flood of connections and make them, for example, remain in the fin wait 2 state, fin 1 state, last act, or whatever. Again, why would you use, for example, these states as opposed to the established state? Because depending on the particular state that those connections remain in, kernel mitigations might or might not apply, and application mitigations might or might not apply. The way in which you select the closed mode is with the closed mode option. So you specify closed mode, and then any of these keywords after that. So let's try to use the TCP6 tool for connection flooding attacks. So among the possible options, let's say the most well-known, if you want, is to perform a SYN flood. The idea with the SYN flood is essentially that you are going to create lots of connections in the SYN received state at the target system. The kind of parameters that you have to specify, this is the network interface. This is the source prefix. So the tool is going to spoof lots of IPv6 addresses, or if you want, it can. I mean, it can spoof lots of IPv6 addresses. This is the target system, and this is the destination port. For SYN flood attacks, that port of the target system needs to be open. So, well, if it's a web server, you'd probably target port 80 here. But the idea again is that it has to correspond to a port that is open. And the other parameters that you might care about, this one, F and Z, specify essentially the rate at which you establish connections. So this means that every second you establish 100 connections. So indirectly, it specifies the rate, okay? That means that every second you are establishing 100 connections. So let's see if we can get this to work. So this is the connection table at the system that I'm going to attack, okay? There are just open ports that you can see here, like port 22, port 19, and a number of ports, but there are no connections in, in any other state other than listen. And if things work as expected, let's put things like this. You see? Let's stop this. So what I got here is lots of connections in the send receive state. Okay? This is a tradition. I mean, there's nothing new here other than it's an IPv6 based attacks. These attacks are from 1997, so to speak. Okay? The only specific thing here is that it's an IPv6 implementation of the attacks that were performed at the time on IPv4. Okie dokie. So those are SYN flutes. But then there are other kind of connection flutes. So for example, I was saying before that I could, for example, try to flute a target system with lots of connections in the established state. Okay? So in the case of the send receive state are connections that have not yet been properly established. So we could try to do that. Let's say connect. Oh. What's going on here? That's probably because I have issues with the routing table. Let's see. Let's go again. There you go. So you see all these connections in the established state are connections that I'm spoofing right now. I'm going to run this again. Oops. These are connections from the previous attack, right? And these are connections that are in the established state that I'm creating. Now, if you look at my own system, because you might say, okay, well, but you're creating connections in the established state at the target system, but what about your own system? Maybe you are tying resources on your own system too. Now, if you look here, you can see that I don't have those connections at all. These are these are other connections, but I don't have connections in the established state on my system. The reason for which that happens is that if I were to establish the attack connections with the kernel, like using the sockets API, of course I would get connections on my own system too. But I am establishing those connections by spoofing the packets. So my own kernel never gets to know about the connections that I am establishing. Okay? So the benefit of this is, or the benefit of fluting a target with this kind of tool as opposed with like a normal application on your system, is that you don't tie any resources on your own system. You only tie resources on the target system. And then you can also do other things, such as let's see if this works. So what I did here, if you look at the command that I'm running, I specify that I want the connection to be in the last ACK state, okay? So I'm not just flooding the target, but I'm saying, you know, those connections that I'm, you know, that I'm flooding that target with, I want them to remain in a specific TCP state, which is last ACK. And if I go at the target system, you see that the connections are in the last ACK state. This is something that I've not seen in any other tool. I'm not saying that it's like extremely awesome, but it's something that I've not seen implemented, okay? The nice thing, again, is that if you have some application, like a web server, that, you know, take cares about multiple connections from the same prefix or the same IPv6 address, or in this case, it will probably not be able to enforce those mitigations, because when a connection is in the last ACK state, it's the kernel handling the connection and not the application, okay? Of course, this is, you know, a flood of connections in last ACK, but you could flood the, you know, the target with connections in virtually any state that you want. I mean, you just need to specify the close mode in this way. So I could, you know, specify Fingway 2, Fingway 1, whatever you want. Other things that, you know, this tool implements. It actually implements more attacks, but I'm describing just a few of them. Many years ago, there was a guy called Stanislew, which described like a very cool attack that you could perform against a TCP-based service. And the idea is pretty simple. So let's say that I have a web server there. I'm assuming that you know the basics of TCP flow control, so to speak. Let's say that I have a web server there, and I'm the attacker here. One thing that I could do is request like a file to that server, okay? And right after I send the request, I advertise a window of 0. If you don't know what a TCP window is, it's essentially a way of, you know, doing flow control. So you are able to tell the other side of the connection how many bytes you are expecting to receive. Now, what happens in that case? If I request a file, that system will, you know, start or will try to start sending the file. But if at the same time I advertise a window of 0, the system will not be able to send me anything. Now, what happens in that case is that if you flood this, if you do that, but with many multiple connections, now you are not only tying a lot of resources on the connections themselves, but also on the send buffers. So now the server not only has lots of connections, but now has lots of buffers with data that it wants to send you, but it can because of, you know, the window that you advertised. I will not get into the details of this, but just describe that this is the way in which you can implement the attack. So if you look at the command, it's very similar to the ones that we used for the previous attack. The only difference is that in this case, you specify with the data option a payload. And in this case, as you probably know, this is an HTTP request. So that means that for every connection that we are spoofing, we are also sending an application request. Again, this doesn't tie any resources on our local system. It's not that we are using the sockets API. It's all spoofed packets. Okay, so it's extremely like lightweight for us to perform this attack. Now, if you perform this attack against some sort of server, you will see that you not only end up with lots and lots of connections, but if you check, for example, if you use the -m option in netstat, you will see that there's lots of, you know, memory employed for the sockets and buffers. Okay, so the TCP stuff, I mean, I usually think of TCP as a protocol that usually people that focuses on the TCP stuff doesn't work on anything else. If you follow TCP related stuff, there's even people that just devote to congestion control, for example. So that's like a very, let's say, kind of like complex and specific protocol. So rather than, you know, continuing with possible attacks that you could perform with this tool, I will just provide this pointer. This is not really a paper, like a technical report that I published in 2009, which essentially covers like virtually every attack technique that you can think of for the TCP case. Now, the nice thing now is that at the time we published this, you didn't really have the attack tools to reproduce the attacks. So we came up with the attacks, but we didn't give you tools to actually be able to perform them. Now, if you take the ideas of this document and you try and you implement them with the with the TCP tools, then you can reproduce the attacks that we are talking about. Okay, this presentation goes till 5? Till 5? Yes, perfect. Okay. At some point in time, I say, okay, there's a TCP6 tool, but what about UDP? So essentially, we produce a UDP6 tool which can send arbitrary packets. For example, you can use extension headers. You can send multiple packets to a specific destination. Like say, well, I want to send lots of packets to a DNS server. You can use lots of filters. That's something that every tool of this toolkit supports. So, for example, you can say, well, I only want to respond to packets that come from this or that other system. I only want to respond to packets that use this or that other port. So it's very easy to customize what you respond to or not. And this tool also has a data option, which allows you to send specific, attack payloads to your target. This is new in this version of the toolkit. I don't really have like a demo for this UDP6 tool. The explanation that I can give for that is that, I tried to perform like, you might recall the echo, what was it? Like the chargen and echo attacks, where you can cause like packets to bounce from, from one endpoint to another. So you spoof a packet to the echo service, and that service automatically responds with echoes. Now, when I try to do that with FreeBSD, Linux, and so on, they all implement mitigations. So I don't know if there's like a way to circumvent that, like put the services run on different ports, but eventually I had spent like more than an hour trying to do that, and I say, okay, forget it. But if you can come up with some idea that you say, well, I need to send UDP packets to this or that system, this is the tool that will allow you to do that. Okie dokie. Then there are other tools that, don't really do any fancy stuff, but that implement stuff that at the end of the day you usually need to do. So, for example, at some point in time, I was meaning to, do measurements with different kinds of systems. I'm going to describe the specific measurements that I was going to do. So I was faced in a situation in which I wanted to, obtain a list of, or I had like a list of domain names, and I wanted to, get the IPv6 addresses corresponding to that list of domain names. I mean, that's something that is, let's say, pretty simple. You have a file, like a TXT file, one domain name per line, and you want to convert that to a file that has one IPv6 address per line. You could probably do that with scripting. Actually, you have to do that, or you can do that with scripting. But since that's something that is very likely that you will need to do, we included a script in the toolkit itself so that you don't need to implement the script yourself. So the script6 tool can do batch processing of domain names and IPv6 addresses. So for example, if you have like a file that has, for example, multiple domain names, by using the script6 tool, you can map those domain names to anything that you want. One simple example could be, let's say, let's go to Troopers. So let's just say that I have this file. Okay? And let's just say that I want to obtain the V6 addresses for each of those domain names. So what you do is, script 6. That's funny. Yes, you're right. And what about the other one? The funny thing with demos that you do on the fly is that they never work. And what about IETF.org? It could be, wait. There's probably some fucked up there. Well, what happens with IETF? That's a very good question. But there's probably a bug fix in. Yeah. What? Let's see. Well, I'm doing something wrong there, which I don't know what it is, but essentially the idea is that for each line that you have, each domain that you have in your file, you get as a result this kind of output, okay, where you get the domain name with a comment. All of the other tools in the toolkit will ignore lines that have a dash at the beginning. So that means that you can use this same file for any of the other tools of the toolkit, because they will ignore these lines. So now you get, like, for example, 2 IPv6 addresses of the domains that you had there. Now let's say that you had that list of domain names, but you now want to obtain the name servers for those domain names. So what you could do is do something like this. Okay, so what I did is, I know that's clear. So what the tool did here is for each of the domain names that it had in the file, it obtained the MX records. Okay. Now let's say that usually you just don't want the domain names, but you want the IPv6 addresses of the names of the mail servers. So what you do is you pipe the tools in this way. So what we are doing is we start with the domain names. With this command, we get the MX records, like the names of the mail servers. And then with this other command, you get the corresponding IPv6 addresses. So what the tools are doing there is start with the domain names, then get the MX records, and once they had the MX records, they obtain the IPv6 addresses. You can do the same thing for the NS records, which is the name servers, okay? I mean, there's no magic here. It's just like a script that takes, each line and then tries to obtain specific, DNS resource records. Now, if I wanted to, obtain the IPv6 addresses of the name servers of those domains, again, I do the same thing. Script 6. Get quad A. Okay? So the reason for which I needed this was because I was doing measurements, or actually what I did was I downloaded Alexa's top 1 million sites list. So I had the list of domain names there, and I say, well, I want to measure different kinds of systems. Web servers on one side, so that means just obtaining the quad A records, then measuring name servers, which means get the NS records, then the quad A records, and measure mail servers. Get the MX, and then from the MX, the quad A. Nothing Greek here, but it's something that probably, if it, if it wasn't implemented in the tool, you'd have to implement yourself. Okay, we did this. We did this. Other stuff. Eventually, when we were doing, measurements, we needed to find out what was the autonomous system corresponding to a specific IPv6 address. That's something that you can obtain with, like root view or whatever you want, but we implemented a tool which you can give like IPv6 address, and the tool can give you either whatever you want, like just the autonomous system number, or not just the autonomous system number, but all the other corresponding information. So let's just say that, let's go clear, says, oh. ¿Dónde mierda está? So let's just say that, what we wanted to say. So I'm just obtaining, Google IPv6 address, or one of them. So if I want to know what's the autonomous system number corresponding to that address, this is what I do. And the tool just tells you that the autonomous system number is 15,169. Now, you can get more information, because that's just the autonomous system number, but the tool can get like the full thing. So it obtains not just the autonomous system number, but what's the prefix to which that address belongs, what's the rear that actually handed that part of the address space, and what's the organization to which that part of the address space belongs, okay? Again, there's nothing like crazy here, but it's something that is useful, and I don't recall having like, something straightforward as this. What else? We did this. Oops. Other stuff. Of course, you have probably used like an IPv6 version of traceroute. The only problem or limitation with the traceroute implementations that you probably have on your operating system is that they don't support extension headers. Okay? So you can probably use like different proof packets, but if you want to try, if you want to do a traceroute but employing extension headers, you won't be able to do that. So we implemented the Path6 tool, which allows you to do a traceroute, but using extension headers if you want. So as an example, so let's first try a traceroute without extension headers, okay? Now we can, I think this has -b. If you specify, for example, the -u option, that means a destination options header of 8 bytes, okay? And the destination option headers is just going to have like padding options. So it's just, occupying space but not carrying anything special. So that probably means that they are being dropped somehow. Oops. So, but you can tell the difference that in the previous case, without the extension headers, we will be able to get to the final destination, whereas in this case you can't. Again, if I run the tool again without the -u option, you do get to the destination, okay? You can also use other extension headers, like, for example, you could use, it's not going to work, of course, because even with one it doesn't work, but you can use 2 destination option header, one after the other. Same thing. This tool, Path6, also allows you to send different kind of proof packets So other than sending ICMP echo request messages, you can send TCP segments, UDP datagrams. There are like multiple options that you can use for the probe packets. You can set the payload. You can, for example, fragment the probe packets. It's extremely flexible. There's another tool that I produced at the time. So many of these tools that I described, like in the last few slides, had to do with the goal that we had of measuring in the internet, in the public internet, the extent to which you could use extension headers, okay? So what we wanted was to grab like a list of public servers from, for example, Alexa's top 1 million sites, and we wanted to measure the extent to which you could send packets with extension headers to those systems. Since there wasn't a traceroute that supported extension headers, we had to implement all of this. But the goal eventually was, again, to measure the extent to which extension headers were supported. Now, let's just say, for example, that you are using packets with extension headers to connect to some system, or either because you want to do a penetration testing, because you are measuring that, or whatever, and you find that your packets don't get to the final destination, okay? So, for example, you connect to Google without the extension headers, and everything works as charmed. Now, you also employ, let's say, destination options, and your packets don't get there. So what you probably want to know is where in the network your packets are being dropped. This is not really a security thing, but more of a troubleshooting thing, okay? So what we did is implement a tool that is called Black Hole 6, which essentially tries to find out where in the network your packets with extension headers are being dropped, okay? So before actually getting to the explanation regarding how the tool works, let's try to use it so that you can get a feeling of what the tool is about. We can also do. Okay. So let's try this and see if it works. So what I'm trying to do here is to find out whether packets with a destination option header of 8 bytes work towards this system www.gont.com.r, okay? In this particular case, what the tool is showing, let's run this again. What the tool is showing is that there are no packet drops. So that is, the tool tries to send packets without extension headers, everything works perfectly. Then it tries to do the same thing with extension headers, and everything still works perfectly, okay? So what it says is that when we are trying to connect with this destination system, this is the autonomous system to which that address belongs. Now, when we employ no extension headers at all, this is the last system to respond, which is the actual target. When we employ a destination option header of 8 bytes, again, the last system to respond is the target that we were trying to get, which means there are no packet drops at all. Everything works perfectly well. Now, let's try, for example, the same thing, but with a different system. Oops. Obviously, the reason for which I'm trying Google is because Google is well known to drop every single IPv6 packet that employs extension headers, okay? So in this case, you are going to see packet drops. Now, if you look at the output here, which is this part, okay? What you see is that we are trying to get to this IPv6 address. The autonomous system belongs to Google. The last node to respond when we don't employ any extension headers is that target itself, which means that our packets are getting there when we don't employ extension headers. But now, when we employ a destination options header of 8 bytes, the last system to respond is this one, which is not the one that we were trying to get to, okay? Now, who does that system belong to? Well, when you try to map an address into an autonomous system, things can be like a little bit ambiguous, so to speak. So the tool tells you two different options. In one of the possibilities, there's an autonomous system that it cannot identify. So that's why it says unknown here. In the other possible case, it's Google. Of course, I know that in this case, it's Google itself that is dropping the packets. As soon as packets get into Google's network on the border, they are dropped, okay? I think, I'm not sure, but I think that kernel.org had the same problem. What problem? We can try kernel. So in this case, no packet drops, things are fine. Let's see with fragments. So in this case, it's fine. I will try from here because I seem to recall that kernel.org was filtering this kind of thing. Oops. No, in this case it's fine. At least some time ago, kernel.org, some network that was, like right before kernel.org, was dropping fragments. I don't know if they changed that or what. But again, the point with this tool was that it allows you to easily identify what's the node that is dropping your packets with extension headers, and it also gives you information about the autonomous system, what's the organization that system belongs to, and so on. When it comes, you might wonder, well, how does this tool get to know, what's the system that is dropping the packets? It's easier. This is not that. So this would be like the easier explanation. So what the tool does is, first of all, it runs like a normal trace route without any extension headers at all. So that would be like the output on the left side, okay? Then what the tool does is it runs again trace route, but now with extension headers. And it gets this other output. Now, assuming that packets follow the same path, which could or could not be the case, but usually it is, if we find that the last responding node, when we send packets with extension headers, is this one, well, usually the system dropping the packets is the next one. Okay? So this is what the tool does. I mean, when you run Black Hole 6, it first runs trace route in this way with no extension headers. Then it runs trace route with extension headers, finds that this is the last system to respond, then comes to this other trace route, looks up, the same entry, this one, but here, and then it assumes that the system dropping the packets is the next one in the list, okay? Of course, the idea is that it does that automatically for you. You could do it, manually, but it does that automatically for you. And of course, once it identifies this system, it obtains the autonomous system relevant information and so on. There are a number of things that are not that easy. For example, the tool was informing what was the autonomous system to which the dropping node belongs to, okay? Now, looking up the autonomous system is not hard, okay? Now, the problem is that you have different scenarios. So, for example, you could have two autonomous systems, like in this case, where the address space that is being employed for the peering session is being provided by this autonomous system. Now, you have this other case in which the address space is being provided by this other autonomous system. And you could also have a case in which the address space is being provided by someone else, okay? That's why there is some ambiguity when, Black Hole 6 informs you of the results. In many cases, the tool will tell you, well, the autonomous system could be this one or this other one. But, since there is ambiguity that comes from this, not in all of the cases, the tool can tell you, I'm 100% sure that the autonomous system that is dropping the packet is this or that other one. We did this one already. Let's see. So, much of all of these things that I have described, like, implementing a trace route that supports extension headers, trying to find out what's the system that is dropping the packets, again, we implemented because we wanted to measure on the public internet the extent to which packets with extension headers were supported. So this part of the presentation will describe, what's the process or what are the tools that we employed to actually make measurements at the kind of like large scale. Okay. So the idea again was to grab like a list of domain names and try to figure out the extent to which packets with extension headers could get to those domain names. These are some of the tools that we had to use or implement in order to be able to perform those measurements. Well, first of all, path 6, because it's a trace route implementation which supports extension headers, that was necessary. Then there were these scripts that were needed to process the Alexa's top 1 million site. First of all, this one, extremely simple, but the thing is that when you download the file from the Alexa site, it's not really a list of domain names, but it's a comma-separated values file. So it has a rank, a comma, and then the domain itself. So we needed a script to just extract the domain name. Then these scripts here to obtain the IPv6 addresses, the IPv6 addresses corresponding to name servers and mail servers and so on. Then we also employed the address 6 tool. It's a tool that is not really new in this version of the toolkit, but it's necessary for this. Address 6 allows you to do like virtually everything that you could possibly want to do with an IPv6 address. For example, if you have like a list of addresses, you can tell the tool, well, I want the tool to filter out any addresses that are not global unicast addresses, for example. Or if you have like a list of IPv6 addresses, you can tell the tool to remove every address that is a duplicate. So you can come up with a file that has lots of addresses. Some are duplicate, some could be multicast, link local, and so on. And you can filter out all of the addresses that you wouldn't want and just keep those that you like to do the measurements. Then we produce this tool or this command of the script file, which essentially what it does something very similar to what the Black Hole 6 tool did, but it provides output in a way that is easy to script. Okay, so with Black Hole 6, it provides output that is useful for a human being, so to speak. But in this case, we wanted the tool to provide output for many different destinations, and for that output to be easy to process with a script. And finally, with this tool, get-trace6 stats, what it does is, based on these results, it produces statistics. Okay? So this is what we did. Well, first of all, we obtain the list of, the Alexa's top 1 million sites file. We obtain the IPv6 addresses for web servers, for mail servers, and for name servers. So now we have, for example, 3 different files which have a bunch of IPv6 addresses, but some of them could be like duplicate, very likely. But you also find that there's people that publishes multicast addresses for web servers. I mean, nonsensical, of course, but you find that kind of thing in the DNS. There's people that publishes link local addresses on the DNS, and of course we want to filter all those addresses out. This is how you filter out all of those addresses. Essentially, you pipe the list of addresses to the address6 tool. This command essentially says that you want to exclude multicast addresses and just keep the global unicast addresses. I mean, just consult the manual page for the tool. But if you just use this command, that means remove any duplicates, remove any special addresses, and just keep the global unicast addresses. So essentially in this file, now we have like a clean file that just has non-duplicate global unicast addresses. So we don't want, for example, to measure the same address multiple times, for example. Okay? Once we have like a clean list of IPv6 addresses, what we want is to, for each of those IPv6 addresses, do something similar to what Black Hole 6 tool was doing. So send packets without extension headers, send packets with extension headers, and then try to find out, where in the network the packets drops are happening. And once, we get all those measurements, we want to produce statistics. And this is the command that we can use to produce the stats. I think that I could try to do that with a very, very small file. Where were we? Cat. So these are the domains. So let's just say so now well, the idea would be to have a few more, right? So, Google okay. Oh. Well, I don't know what the hell. Script 6. Get keys. What? Excuse me. Ah, yes, you're right. Now get. Let's see what we get. So now we have more addresses. So let's do this. It probably has duplicate addresses, but I mean, what I want you is to see, how to produce the results. So we are not going to filter the duplicate or, incorrect addresses here. That's something that you do in practice. So if we look at this file, we have at least some list of IPv6 addresses, right? Now, given that list of addresses, if we pipe this to get we are going to now store that in a file, but I want you to see what's the output that command will output. So this is the target IPv6 address. This is the last system to respond without using extension headers. This is the number of hops to that system, okay? This is the last system to respond with extension headers. number of hops to that system. This is the drop-in node, which is there is no drop-in node, and so on. Okay? So the idea is that we in every single line, or for each target address, we are measuring, a number of things, such as what is the last system to respond with or without extension headers, and so on. Now, we're going to store that in, let's say, DOM trace.txt. Because the idea is that we want to have a file that contains the results of the measurements to all of those systems, okay? Once we have that, once we have the file with all of the results for all the target systems, we're going to run a different command which will grab those results and will produce statistics. Let's say. Of course, one thing to note is that when you run get trace6, you can specify not only the kind of extension header that you want to try, but also the kind of proof packet, okay? So you can say, I want to try destination options, in this case of 8 bytes, and the proof packet is going to be ICMP echo. But you can also say, I want fragmentation, I want fragments of 500 bytes, and I want the proof packets to be TCP segments. So the tool supports multiple extension header types, different sizes, different proof types, and so on. So if we look at this file, you see that it contains a list of the results for each of the target systems that we tried, okay? Now, if we pipe this, now what the tool is doing is that for each of these lines, it's going to try to find out, for example, things such as what is the autonomous system that is dropping the packets. It also tries to measure, for example, if the entity that is dropping the packet is the final destination. So for example, when you send packets to Google with extension headers, you want to know if it's Google itself, the autonomous system dropping the packets, or some other one. So these are the stats that we got. If we look up, boop, boop, boop. So we have 4 valid entries that could be processed. In 100% of the cases, it was the final destination, the system dropping the packets, so it wasn't some intermediate autonomous system, but actually the final autonomous system, the one dropping the packets with extension headers. The tool also tells you the best case and the worst case scenario, because as I said before, there's ambiguity when it comes to detecting the autonomous system. And it also tells you what's the autonomous system that is dropping the packets with extension headers. Okay. Tomorrow, when I present, I will be presenting, some of the work that has been happening at the IETF when it comes to IPv6 security. Part of that will include results of measurements of this sort when performed to the list of Alexa's top 1 million sites. Okay. What I try to show here is what are the tools and what is the procedure that we follow in order to produce the results that I'm going to present tomorrow. But the idea here, or what I would expect you to get from the output of these statistics, is that starting from a list of domain names, which is publicly available, such as Alexa's top 1 million site, you can use all of the tools or part of the tools that are in this toolkit. to produce a list of target IPv6 addresses, and then with the tools that are included in the toolkit, you can perform your own measurements when it comes to the extent to which extension headers are supported in the real world. If you follow the V6 Ops list of the IETF, there's currently some discussion going on exactly about this. So there's a document that we published that essentially summarizes these results, and the IETF is essentially discussing that. So some conclusions, there are actually not that many conclusions that you can derive from this. One of them, which was my personal conclusions, is that when working on tools, that would be like my conclusions for working on this version of the toolkit. Portability is way harder than it should be, or than I expected myself. And the other thing, which is nice to some extent, is that the more you use a toolkit, the more bugs that you find, and the more you can improve the quality of your code. So I found myself using the tools a lot to do measurements or reproducing attacks and so on, and that's essentially what led to many of the improvements that you will see in this version. The other thing is that there's lots to learn through practice. That's nothing new. But when it comes to things such as, for example, the extension header stuff, that is stuff that we were discussing in the last few slides, I got myself, let's say it was like quite a surprise to me when I started doing measurements on this kind of stuff, because, for example, I expected extension headers to go more easily on the internet, and then, for example, I ended up finding that there was a quite high drop rate when it came to extension headers. Also, when it comes to discussions that you have in the security community, many times people expect to be able to use extension headers for evading security controls. But truth is that in practice, if you try to do, let's say, an attack or a penetration test of a remote site, usually it's not useful for you as an attacker to employ extension headers, because since they are extremely dropped on the internet, that means that your attack packets will probably not even get to the destination. So among of the things that I learned myself was that even from an attacker's point of view, extension headers are not that nice. Yes, if you could use them, you could, let's say, evade network intrusion detection systems and so on, but in practice, with many sites, your packets get dropped way earlier than they get to to your target. If you use the toolkit, please report to us whether that's bugs, whether that's missing features, like things such as, I tried to perform this or that thing with the toolkit, but I didn't find a way to do it, or the feature is missing. So if you do that, that will probably lead to improvements. I don't know if there are any questions. No? Well, if you have them, well, first of all, the acknowledgements, the list was incomplete, to all the Troopers crew for taking care of lots of things. I particularly probably tried, without intention, but was completely bad at response times, bad at virtually everything. And even then, they took care of everything, from getting me from the airport to the city and so on. If you have questions, feel free to either talk to me on the corridors or in the dinner or whatever. That's my email address. And if you're not subscribed, there's an IPv6 hackers mailing list. Many, if not most, of the people that work on V6 security are subscribed there. So that's like a nice place to share V6 security or IPv6 low-level stuff. So thank you.